Hi, everyone. I guess we'll get started here. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Bate. I'm with Atlanta Functional Programming. Today, we're going to continue our exploration of the, honestly, this is surprisingly awesome uh, and surprisingly mature Coalton library. Last week, this library, I've been exploring it, and honestly, there's just a lot of stuff that's in there that I kind of thought that it would be in some, nascent stage, but it's actually quite mature for being a pre 1.0 library, which sometimes it's a 50-50 shot for projects, but in this case, it's very, very, very well done. I got to give hats off to the Colton developers for at least the experiments that I've been doing. As we continue our exploration, today we're going to be discussing specifically the data types that are available, how to generate parametric algebraic data types as specified in the introduction to Colton library. As I mentioned, this is a README document that covers a couple things, but I'm just kind of like going off on it as a basis and getting, providing you guys some additional examples from what's available and what's not available. After talking about some of the data type stuff that's available according to this document and exploring specifically some of the number support and things as well as list. We'll get into a little bit more about static typing and even some pattern matching examples. And you'll see a lot of some of the core library overrides that they wrote, some of the forms that they wrote specifically to the Colton library that m- provided kind of a motivation of separating or even encouraging you not to import or use package the main Common Lisp package in your packages when you're defining your Colton libraries. Just because some of the forms that we're going to be seeing today are actually overriding or shadowing those particular core forms, which will cause all sorts of havoc when you're actually dealing with Lisp code, just because of name conflicts that are going to be present. After that, I'm just going to briefly, time permitting, touch base on type classes. I'd like to get into the type classes a little bit, just in the sense, so that we could start getting prepared for eventually what I'd like to talk next week, which is more on the three type classes that are available in Colton that will allow us to essentially do what we can do in Haskell, which is primarily define functors, applicatives, monoids, semigroups, and monads, and all sorts of things like that. So I'm just trying to get us at least up to stuff so that this way, if all is good, we can get started on the functor discussion, both in this particular group as well as in the Haskell study group, which I run also on Thursdays from 7:30 to 9:30 p.m. Eastern time. Um, Before we get started on our discussion on data types, a couple of interesting things that I wanted to kind of point out, thanks to some help that I had from one of our my co-organizer. We were exploring some stuff inside inside Colton last week, and I thought I would share with you a couple of interesting things. Um, so I mentioned to all of you before uh, that um, Colton ends up allowing us to do function composition using two different types of composition based on the applicativity of the composition. You may recall the nest and pipe operators I've introduced last week, where you can take a couple of functions, let's say a square and a double function that will, square the appropriate value that's passed into the function, as well as the double, just doubling it, and we can actually pass in, square and double accordingly this way. As it turns out, and before I get started here, let me just quickly load up our project. As it turns out, we can actually see some of the interesting things that Colton does behind the scenes, specifically with the nest and pipe operators. Because if you remember, Colton specifies these composition operators as macros. Now, if you wanted to use a composition inside of a function, like a high order function, like say map, you would have to actually, of course, use oops, the compose uh, function versus the pipe and nest macros. Um, to illustrate something that the interesting thing, and let me just go ahead and do this so that it's pretty useful. Let me first set package to our um, AFP Colton overview package, which of course has those of you recall, it's only using the Colton and Colton library, which means you don't have access to the CL namespace for the time being. If we actually go and expand this, this can kind of show you behind the scenes of what's going on with the nest and pipe operators. We could actually do the macro expansion directly by calling macro expand one, but of course, because macro expand one doesn't exist in this package because we're not using the package, we're going to have to explicitly prefix it with the CL colon thing so that we can actually get access to the exported symbol. But we can actually then call macro expand one, as we can see here, and we can just call nest um, double square x, and we could see that what it does is it actually calls as expected um, nest double square x. But if we do cl macro expand one on um, pipe, where if you remember, pipe is kind of the equivalent of that pizza operator that some of you maybe notice popping up in some libraries, um, as well as being the inspiration for things like what you would see in say the shell. As well as the pipe operator is commonly now in C++ if you're doing function composition or ranges inside C++. If you actually do this, what this does behind the scenes is the same thing. It actually converts the same expansion. So what this does is first it will actually convert a pipe into nest, and of course, if you generate you know uh, CL macro expand to another macro expand one, you could see that this will actually ultimately convert this to what we had before, which is just a double square x. Just telling you that these are fundamentally equivalent, and a pipe is doing nothing more than doing a reverse on the function calls and then passing the rest of those calls over to nest so that the nest macro does what it expects to do, which is actually generate the appropriate S expression syntax that will go from rightmost function, which is the innermost function, and going outward to generate the final S expression that will ultimately be evaluated by the REPL. The one thing to note here is every time that we are returning from pipe or nest is and this is something I did not call out explicitly last time, is the fact that we are actually getting a true or false from the macro itself. This is something that I noticed before. Normally, you wouldn't necessarily see that kind of like true or false coming in. Like, let's say if we end up doing a CL macro expand one on our common CL when 4 is less than 5, CL print hello. Okay. This doesn't necessarily print out, oh, actually, it's doing what I expected to do. It's actually printing out the true or false. Let me actually go into set package CL user. I actually thought for some reason it did not, it ate that true or false during a macro expansion. Just do this one time. That up. Oh, interesting. This means that we can actually get the successful parse from the expansion or a nil. Um, that's interesting. Okay, I'm gonna make a mental note of that. That's neither here or there, here or there. The return value of the code. I just I found that's a particular something I just noticed now, which is kind of sometimes sometimes the stuff that you end up figuring out while you're coding tends to be very different. Um, okay, so we have a question here. Is there still an active? Yes, I will post. There's a question on our GitHub repository. I will post any additional examples that I provide on Atlanta FP. That is our organization, AFP organization repository where we are hosting all of our tutorials as well as workshops. I did not explicitly make a submit for the code that's going to be presented today, just because some of the examples I tend to do on the fly, but I will take some of these examples. Some of them are already straight up from the examples that are available in the Colton documentations. There are some additional examples that I've kind of come up with myself. I will go ahead though and post both of those over into our Atlanta FP GitHub repository, which is located at github.com/AtlantaFP. You can go there and look at all of our actual projects and so forth. So I'll go ahead and post this after we're done today. Okay, so and folks who are on the stream, I don't think I have to mention this again, but as usual for anybody who's just joining us, we tend to be very ad hoc and free form in this study group as I'm presenting some of the materials. So if you do have a question, feel free to go ahead and post it inside the live chat. Or if you are watching this stream and have a question that you'd like to have answered on the stream later on, go ahead and post the information on the YouTube comments, and I will get back to them as soon as I can. Hopefully by the next stream, if you depending upon when you guys post it, of course. So let's get back to the other package that I was on, Coalton review. Okay. So we also talked last week about type restrictions and defined, a simple example type here with our generic tree. Okay, this is we kind of what we ended up here is the introduction to the parametric polymorph algebraic data types discussion, but we didn't really dig into a lot of the discussion that's here. Um, One of the things that you probably recall, but I will go ahead and reiterate here, is when you're dealing with generic types inside uh, Colton, they're very much the same as Haskell in that if you're trying to create a parametric type, you need to provide a type variable. Now, one thing to note about Colton is Colton leverages the keyword namespace to provide its type variables. So as you can see here, our generic tree that I introduced last week introduces the tree has our um, uh, has a parametric type with the type variable of colon A. Now, one thing to be aware of is this colon A business is not only is it just a type variable, excuse me, but also sorry, I had something caught in my throat. Also, The type variable itself is lowercase, just like in Haskell. Okay. Now you can name technically all these type variables anything. You can have an A, B, C, T, what have you. But just beware that Colton tends to follow the same sort of type variable scheme as Haskell does, in that keyword variables start with colon A and then work their way up the alphabet. Okay. So try to, just, kind of a code construct. Just be aware of that as you are going through the examples and, adopting some of this stuff. Of course, the next logical thing that most people are going to be asking for is how do we go and unpack this, much like Haskell does. Colton does provide the match operator, so you can do pattern matching, and we'll come up with it. I'll show you an example of that later on. But I just want to be aware that right now we'll touch base on that once we get to it. But first things first, we're going to talk about some other data types that are available to you inside Colton. Okay. Um, Colton provides several different numeric types. Okay. So when you're talking about uh, Colton numeric types, you have essentially integers, which we've already kind of seen in the previous example with the 3D point, but we also have um, single float as well as double float, and these both match to uh, single uh, CL single float, and I think CL double accordingly too as well. So if you guys want to see it, you have double float there too as well, and both of these kind of match to both of those equivalent things that are available to you inside of the Common Lisp library. Of course, just as before, when we're defining this, we can go ahead and, use our define int to actually go and use our define form that's in the Colton top level to allow us to specify these guys. And they are the same sort of notation that you would normally expect of common Lisp types too as well. So if you get at these and look at these here, numdf 5.0d0, you can see that this will all work. And then, of course, when you go ahead and do CL print, when you are actually, let's do CL type of, and we do Colton num sf, you could see that these map to single float, double float, and um, our 64-bit integer as well. One second here. Um, okay, sorry about that, folks. Just a little technical difficulty here. Um, In addition to as you can see here, we have essentially 64-bit integers. We have double floats. We have double precision floats and single floats. But in addition to that, we also have some more restricted fixed width point types. So this is particularly interesting to check out. Of course, we could do things like define. Um, We'd have to show you, in order to illustrate this, I would have to show you um, probably a basic signature again. So we've already kind of went through function signatures in um, uh, last week, so I can just kind of show this idea. So remember from last week, to do a function signature prior to defining a function, we have to use the declare syntax. This is much like folks who are coming in from Common Lisp, the real Common Lisp world. This is equivalent to doing like a F definition declaration when you are doing a type declaration at the top level. And it's the same kind of idea. In fact, I think it actually boils down to using an F definition to actually go and define the function definition to provide type information to the compiler. Um, we can always check that though. So we're going to just make a quick declare here, and we're going to call this multiply u32, okay? And we're just going to go ahead and in multiply u32, provide u30 taken and two inputs u32, and return a to object here. Now, and you know what? Let's not make it unsigned. Oh, unsigned just means that, of course, it's going to be an unsigned integer of 4 bytes. But let's go ahead and make this, simple on ourselves. Okay. Um, and I think it uses. Actually, let's even do this. Let's even. I think this would be fine. Okay. So let's go ahead and obviously we need to go ahead and do that, and we do x, y, and we will multiply x times y, right? Obviously, this is all going to pass. And if we try to pass in, oops, this is actually wrong because I'm saying unsigned here when it's really signed. Go ahead and do that. If we call multiply I32 on, say, let's just do this coalton multiply I32, and we provide, you know, essentially, let's go ahead and provide, large numbers so we could throw a type error here. All right. At y, we go ahead and pass this twice. You'll see it complain because the we're trying to pass in an integer and it's expecting a 32-bit integer. So this can show you that obviously this won't work. If we pass in though, let's say I have to go and remember my CL to 32 here. It's 31 actually. 231 is our maximum value because remember it's a signed 32-bit integer. If we pass in this, of course, we won't have a problem. So if we go ahead and do coalton and then pass in multiply I32 with our 1, will obviously interesting. It says that it's still an I30. Let me just do 1 by 1, 2 by 1. Hmm. It still is not inferring it has an integer, a 32-bit integer. This is interesting. Um, this might be another potential limitation of the current implementation that I just did not encounter. There are more restricted types as well as fixed unsigned types. I'm going to make a note to see if I could somehow fix this particular thing. It does show that the type checker is working, but it doesn't seem to be doing what I expected to. I'm wondering if I have to explicitly wrap this guy. Let me see if I can wrap this guy as an I32 type constructor. Let's see. I32 1 I32 1. Let's see what happened there. There is no type constructor like that. Okay, kind of figured that that wouldn't be the case, but who knows? Um, okay, so this is telling me that there might be still a kink in using some of their integer types. Uh, I will make a note of it, and hopefully, if the Colton guys are watching, uh, if I'm doing this wrong, please correct me, and I will go ahead and make a follow-up video. But for now, this is something that's particularly uh, interesting that it will not. Ooh, wait, I think I figured it out. I have to use past this. I have to use the operator just like Common Lisp. All right, let me just see if this will work. Multiply I32. Um, uh, I32 1 the I32 1. Um, nope, the DAW operator is not working as I thought it would. Um, but okay. So one thing that I want to show you that I think is pretty neat because they actually went ahead and implemented this, and I didn't realize this until the next thing. And of course, like I said, this is what what I'm seeing here for the casting here is something that I'll take a look into and see. I think it might be just a particular issue with the current version of uh, their uh, their library. Like I said, it is pre 1.0, so there's stuff that I might be uh, 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 um, like I said, the one thing about this that's particularly interesting is there is if you want to go and look at a type signature now inside the Colton space, they actually overrode type of so that you can actually go and look up a specific, let's say what we specified, and it will actually generate the type signature for you, much like T if you're coming from the Haskell space. So for folks who are looking at this, if we generate a simple function, and I think we already have one in this library in their example, um, that we did not specify. Um, yeah. So if you have a generic function like our square function, we can actually see that if we type in square here, it's going to go ahead and recognize what the top level operator that you've provided, and it will infer what the type is. Um, so let me do, sorry, not add, double. You can see that these are all integer colon integers. Um, and again, they're inferring it based on the operator that you're using because it's going to reduce to whatever uh, core operators leverage there. Um, most of the functions, let's say plus, you can see the generic operators will take in anything that leverages the uh, the coalton type classes. It will go ahead and create the appropriate unified type signature. Now, for common Lispers who aren't familiar with Haskell, I think I can. I'm going to give you kind of a brief reading of all this. Is um, what this function signature is telling you is a universal quantification. That operator that's in the first part of the line is basically saying for all types A, the type A must adhere to the numeric type class, and only if it satisfies that contract will it be able to actually execute this function. They'll take in the type variable, two type variables of A, and then return the same type of A. All right. So what this is expecting is whatever the arguments are passed in to the plus operator, um, the two arguments both have to be of the same type. Number one, that's what the signature is telling you. Number two, the type has to actually satisfy a contract, which is called the type class. And again, we will go ahead and talk through the type class stuff as we go on. Um, Type classes, if you want, in a nutshell, is basically a nothing more than an interface. You could think of it this way, but it's an interface for types, for the types to be satisfied, and of course, for the particular function, if it's a parametric function, to be instantiated. Okay, so in the case of the type class, you need to have an implementation of the type class methods defined for your particular type. And when we talk about type design, this is a very important thing to recognize when you are dealing with type classes coming from the Haskell space, especially if you're trying to leverage coalton in the static typing way that it's kind of encouraging you to design your systems. Um, One more final thing about type of that I just want to show you is, and again, when we talk about type classes, defining type classes, you'll see this more detailedly. When we unfortunately, type of does not have any sort of way of querying information about type classes. And this is kind of unfortunate. I haven't seen any sort of thing, kind of like info coming in from the Haskell space. And it very well could be that at some point they may specify it, but I don't see anything like that, as you can see here, that will allow you to leverage some of that information. So for the time being, if you are defining your type, your definitions for a particular type class, I would encourage you to look up the signatures and then leverage that. I hope maybe at the Colton library level they may add something, but as it stands right now, I think there's other things that need to be done first before they can add stuff like this. Although it would be pretty useful, especially if you're trying to leverage this for more interactive programming for your type system, but at which point you may as well just write stuff in Common Lisp. Are there questions about type of? Okay. Okay. Let's go back to, let me see if there's anybody on the live stream asking questions. All right, cool. Just keep that in mind. And that around. Okay. Numeric division. Since we're talking about numbers right now and function signatures and things like this. Obviously, the next thing that we'd probably want to look into, that obvious thing is since we already talked about plus, minus, and times, essentially, which all adhere to numeric type class. Um, One logical question for folks who are coming in here to Colton, just like because it's there in Common Lisp, is why doesn't the numeric type class provide a division operator? And obviously, if you are thinking about the implicit type casting and things like this when you're dealing with numeric values inside Common Lisp, it should be obvious that the division operator is difficult to define, especially for the numeric type class, because integer division may not be what you want. It may be one of different types of division. You may want to, in the case of Common Lisp, you could provide return a rational number. You could return a double or single float value, and so forth. Um, The one thing to note about this is of course then is because of this you need a different type of signature that's available. And what Colton has done is essentially it defined essentially a type class for dividable. This is very much in line with, I think if I remember correctly, there's something equivalent like that in the Haskell type classes right now. It's kind of escaping my memory. And what this is doing is it takes in two different types, A and B. They may be of the same type. Uh, of course, the A type is going to be the type for the dividend and the divisor, and the B type is the result, the quotient that's going to be provided there, and could be optional. One thing to note about A and B there is the dividable type class is going it requires both type A and type B to be dividable. Now, folks reading this predicate here, that multi-argument isn't saying that it's taking A and B and making sure that they're compatible with each other and that they're dividable. No, it's taking essentially uh, A and making it's saying that the two items of type A could result in a item of type B. All right. Um, that dividable type class essentially is saying that A and B should be able to switch between each other, but and dividing A by its any A's by themselves and so within the dividable class, it'll return something of the other type there. But it may not return something. That's why in this particular signature, you are noticing that there is something called an optional signature. That means you may end up not getting something, and this allows us to deal with potential error conditions. All right. Um, this is the default default divide operator that's available inside of Colton. There is a version apparently that you could use that may not return um, optional. It may actually throw an exception. Um, and of course, if you want that, you could certainly do so. Um, the one thing to be aware of is um, if you attempt to do that, just make sure that the appropriate error handling is put in place. So let's quickly just try the expression here just to show you what this is going to do. If we divide 1 or 2, you're gonna should actually throw an error, and yes, it throws an error as it does, and that's because you have to actually explicitly constrain the resulting type, because it can't infer what the return type is here from the expression. So to do that, you have to do what I was trying to do earlier with our And in fact, that's probably why we're having some issues with our integer example. You have to actually go in and do the, and then specify that you want this to be double or single float. Let's say that we want this to be double float. If we do that, then obviously, hold on, I may be doing this wrong. It's going to return an optional. Let's say that this is going to be, let me see if I can do this. Optional double float. Integer, these contents, and coalton. Let me just double check here. Um, let's see. Let's see if this will work. Let me try this double float. This is there. And it says that we could actually specify. Okay, maybe I have to specify. Let's see if single float works. Optional A and single float. Okay. See if I can do this. Just make everything single float for the time being and see if this was defined on this. Interesting. Um, let's see. What am I doing wrong here? Let's try. Is that this should actually convert to appropriated things. Um, Let me see. It says that we could do safe divide here. Let me see if I do. Open. Safe. What is unsafe divide doing? Integer single float. Interesting. Let's do this. Let me change this into an integer. See what happens. Decidable integer, integer. Okay, there's a problem here. There's something with the type checker that I'm missing. Let's go back to what we had before. This one is an optional, but let's see. All right. Package different things. Did I mess something up here in? Let me try if I could do this to force a fraction. Right now, it's complaining about the fact that I'm trying to essentially cast off. It isn't optional of type A. what is the optional type class inside coalton? That is the interesting part. Because I don't want to include the matching syntax unless I really have to. May have to do that here in this case. Okay, let's do it this way. So one of the reasons why we're having this issue is this is wrapped in this optional A, right? But the way to actually fix this is you can actually technically provide this in a matching syntax. So what you could do is you do match. Match is essentially how we leverage uh, uh, pattern matching inside of Colton. I didn't want to introduce this until we got a little bit closer through going through lists, but lists inside Colton. But now is a good time as any since we're now introducing optional to also handle this. So an optional type has either a some or none, as most folks are probably aware inside using optional in other languages. What that means is given an optional value, you either may have something or you may have nothing. Inside of the Colton library, we have the same thing. We could provide an expression. In this case, let's say we're providing 1, 2. Okay. And this is going to return an optional of some type. Now, do we need to specify the type? Not necessarily. You don't have to specify the actual type of the optional that you're returning. It can be inferred. And in this example, we're going to obviously leverage that to actually go and figure out what we have here. So the matching syntax will take in that expression, then allow us to do patterns. And this is very much like for folks who may have seen, cond syntax, it is the same kind of idea. So you provide the pattern, some, and you may provide some sort of expression here. Uh, and let's do this. Instead of doing it this way, let me wrap this guy. So let me rewrite this. X by 2. And this might actually get messed up because, oops, 1. Because I might be using the wrong syntax to do lexical matching here. Let me do it this way. Colton, go up here. Colton, top level. And again, folks watching this, remember we can. I have multiple top levels just because it's nice to keep things like kind of like together. But let's say that we have an example. Let's say we have a quotient that's defining the result of 1 divided by 2. All right. Um, fail to introduce. Let's say that this is going to be an optional integer. We specified this as being an optional integer. Declare quotient as being an optional integer. Let's see if I can do that. During macro expansion, dividable, fail to reduce context in top level. Wondering why that's the case. Dividable is coming from. I'm wondering if there's a bug here because it is claiming that it has these shorthands, but it's not giving it to me when I just downloaded the latest version. Let me try one more thing, and then if this doesn't work, I'll make a note to try out the different division operators after this. Try. I don't know if I remember doing. Let's see here. Let's see. I tried this earlier, but we'll see what this is. Some result of 4 divided by 2. It should be, even though this is kind of useless, dumb. Some x, and add and wrap that, and then we're going to return the fraction. Let's make this into a fraction. Of x underscore and sorry. And let's go ahead and provide one more thing, which is anything else. Just going to return none. See what happens. Failed to fraction optional B. Okay. This is a type error that's because of the fact that it's not deducing that I'm trying to cast the result of of 1 divided by 2 into an optional. Well, I'm trying to unwrap the optional. Interesting. Okay, I'm going to move on just because this numeric division thing seems like it is a bit, there's some limitations there based on what I'm seeing here. And it doesn't really match what is in the documentation because the documentation claims that the simple example that I showed you all should have worked. And coalton does define the operator. Although it's not showing up here. Interesting. Okay. All right. So let's talk about lists. Lists are inherent to Lisp has as you all know, and any language and statically typed language that's going to be leveraging Lisp will have such a base data structure as part of its library, and coalton is no different in that respect. Okay, so there is a question. When I run divide, I get 0.5, not debugger. Have you defined your package So one of our viewers has made the question. It's like when he attempts the example that I showed, he's getting zero point 0.5. When you're defining your packages, it's very important that you define it using both Coalton and Coalton library. And folks who don't have Coalton installed, just a reminder, Coalton is not available. And I repeat, it is not available inside Quick Lisp at this time because it is a pre 1.0 library. But that being said, it is fairly mature, and all you need to do is clone the repository from GitHub into your local projects folder of your Quick Lisp installation, and then you could use normal quick load to actually load the Lisp library into your running image. So if you define that and define the package the way I specified it, you should be able to reproduce the same issue. If not, please let me know what you've done, because I certainly will openly admit that since I'm working through these examples myself, I may encounter different behaviors. I may not understand something. Okay, so let's try it in Coalton proper. Okay, so the comment is attempt to put it inside the Coalton package itself. Okay, so let's try that. That's something that I have not tried. Uh, Coalton, divide is undefined. So we have to specify Coalton library here because Coalton library is the one that defines it. And let's do 1, 2. Invalid arguments 2 here. So let's do Coalton library safe things. Scribe. Oh, right. I keep forgetting that I'm totally messing up my image. I may have to do a reboot because of the intern symbols now. Sometimes we'll screw up potential other things. So let's see what this is doing. Is a compiled function, divides x by y, returning none if y is 0. Lambda list, the first argument is probably the name. Okay, I see what it is. So I have to do Coalton library, probably specify the type in the first argument. G71, which I'm assuming is probably just the fraction. Let's say yeah, no, let's do single float. What happens? 1, 2. Single float is unbound. Of course it's unbound. It's not of type class dividable when binding G71. Okay. Let's do integer. May have to specify. Nope, in the Coalton library. Let's see. None of these are actually defined in that. Where is this defined? keep that in mind and see what's going on there. Uh, let's see this. So it was suggested that I do coalton the single float by 2. See what happens. Unknown binding in coalton. We go ahead and very well could be that I screwed up my Lisp when I do this. Um, just and let's go ahead and load open proper. See what happens. Set package to being coalton. Let's see what happens here. Coalton form the single float. Okay, that did not work. Let's do this. Coalton library colon. Yeah, that did not work. So comment is just doing this normally without anything. So the easiest way to check this now is probably there was an update that I don't have. So let me go and do a quick thing here. And sure enough, it looks like there was a recent update that I did not get last night. Let me pull this up. Let me restart my Lisp. Sometimes this happens. Text scale, just okay. There. Okay. Compile. Okay. And let me even do, if that's the case, let me do what I had earlier. Let's see if this works. Okay. And it looks like that is actually all going the way I expected to. AFP coalton. Okay. Looks like this is did not get loaded. Okay. Coalton, the single float 2. Yeah, okay, now we have it. So this is what I was trying to show. We have the thank you for the comment that that you had it was working. Um, but this is it's because of a slight update that was made a few days ago that looks like that it didn't grab a core correctly last night. I had to blow away my my Colton directory, do a reclone of the entire project behind the scenes. Um, do a pull more frequently, and if you have a corruption, always start from scratch. Nothing wrong with that. Um, again, like I said, this is a pre 1.0 library, so they are making changes as we go along. One of the nice things about this is now that we have this ability to actually go and specify it, we can actually go and change things. It'll go ahead and create these fraction libraries for you. And again, as you see this, the fraction that it's using is not the same as the rational library that the built-in rational argument that's inside Common Lisp. Just to give you a comparison here, if we do TL user, if we do divide by 1/2, you see you'll get the standard 1/2, and this is of type 1/2 is oh, sorry, my apologies. type of 1 by 2 is going to be of type ratio. All right. I don't believe that that reader macro there that you see above for the fraction is essentially reducing to a ratio. I've never confirmed that. Um, but that is something to be aware of. They are, as far as I can tell, they are two different types. Although it should be nice if they are the same type. That would be pretty cool. Okay, let's talk about two more things. If we got this all working, let me quickly just go through this and then we can go down to the next topic. So coalton allows you to also be able to do standard integer addition. Now, one thing to be aware of to motivate the next couple examples is let's say that we are trying to cast our standard um, 4 by 2 into an integer. You might think that this is going to return an integer, but you would be wrong because of the fact that we'll go back to what we had before. You cannot reduce the context of the integer by integer in Colton. This is a type error, and it's because of the fact that uh, for whatever reason, because Colton doesn't particularly enforce any sort of rounding, even in the simplest integer division cases. Um, because when you're dealing with divide, you are in many cases going to potentially be dealing with numbers that don't necessarily divide exactly into each other. And because of this lack of rounding and convert being able to reduce to other types, you have to actually do the proper way of division, which is using an explicit call to any of the rounding operators that are available to you. Now, in Colton, they have overrides for all the standard uh, rounding functions that you might be familiar with. For example, they have floor available to you. So if you do floor the fraction for 2, you'll see that you'll get 2 accordingly. Additionally, you have ceiling as well as round, all of which are at your disposal. And finally, because of a lot of this stuff is probably going to be frequent if you're doing numerical calculations using the Colton library. And this should be correct now that I have this. You have at your disposal safe division, which handles safe divisions in the case if you do something dumb like provide um, what do the fraction. I don't know if I can exactly show this to you, but we will see. Um, there is let's see, safe division. It's going to ask for, let me see, integer, maybe 3 and 0, and see what happens here. Unknown bounding integer. Let's see why that's the case. Because you're trying to divide. Let's first do a CL describe. Safe. See what I have to provide here. Um, it looks like they claim that it can do the appropriate division by 0 check, but That first argument there, I thought it would be a type, but it doesn't look like it is a type. Um, Function takes in class dividable integer and then values x and y. So this should tell me that I may be doing this wrong. Let's see. Um, Maybe I have to specify it has an integer. So yeah, let me try integer. That's right. Yeah, we did this. Let's see here. One more time. Oop, we'll move on. There's some things about these exact operations that are available part of the library. These are shorthand notations, safe, exact, and exact that I want to show you guys, but for some reason I'm not. These are all 3 argument functions, whether it's safe, it's taking 3 arguments, or exact, it's going to take 3 arguments. Oh, exact doesn't. That's interesting. I thought that this would do that. Interesting. Okay. Let's see. Let me see. Maybe inexact does it. Safe might be one of those where it's trying to have me specify the error check at the in the first argument, but I can't really tell from its signature. So I will look into that. Inexact takes in two. This is our standard um, integer to double addition, but it returns in this case in coalton a double precision float, not a single precision float, or doing any sort of casting on this. So keep that in mind. Um, and of course, you got single division and double division, which will make sure that you cast accordingly. Oh, right. These two here both require you to first provide um, single or precision or double precision quotes. I mean floats. You can't just do. I don't think you can do 1.2f. This is not uh, a our standard Lisp float. That's C syntax. I got to remember that. So you got our 0.5 here, and if you want to use double as well, you have this guy, and this will always do double precision flow, double precision division, and it will always return double precision floats at the end. Okay, so let's talk about lists. Lists in Colton are parametric types. In Common Lisp, they are not actually, they are different. Okay, so I have to tell a slight difference here. When you're coming in from normally languages like, say, Haskell, C, C++, what have you, I think many of the Lispers that are following along already know, but all the new Lispers tend to find this kind of interesting. Common Lisp lists are actually heterogeneous. Okay, they are heterogeneous types. They can each cell can hold any type, which means you can have tuples automatically within the same structure has lists of integers. All right, so the same exact underlying data structure can hold everything. They're all at the end cells. Colton brings us back to more in line with what most statically typed languages treat as lists, which are parametric types where every member of the container is of the same type. Okay. So if we actually look at, for example, type of make list, which is our constructor. I thought it was our constructor. Give me a second here. I may have make Make a list. For some reason it did not do what I expected to do. Describe, describe make list. Oh, right. Sorry. My apologies. I keep forgetting I have to put CL describe make list. Okay. So it might be that to show you guys what I'm talking about, I'm going to have to make a list and then we can go through it. So to make a list, you have to use the make list um, uh, constructor. Let's make an example list of integers that I showed you earlier, 1, 2, 3. Okay. It doesn't really matter. I had 4 there earlier, but you can call it, you can do whatever you want here. And let's say that we create another list. Okay. Let's call this guy, just so that I don't have to type a lot. Um, list 1 and list 2. All right. Very generic list names, I know, but one holds a list of integers, the other one holds a list of strings. If I do a type um, of coalton of X, sorry, of list 1, you will see, oh, right, sorry. If I do a type of list 1, you will see, hmm, known bounded type. It's not allowing me to, that is really weird. Um, hmm. So list 1 does not exist. Oh, wait, list 2, type of list 1. There we go. I keep forgetting that I have to provide the symbol, otherwise it's going to bind it. When you do type of list 1 and type of list 2, um, and this is the only time you may have noticed that um, every other time that I tried to use quote, it actually complained, but type of doesn't. That's because all other times CL quote is being used in a context in which it is not bound to any particular operator because we're not using the package. But this is a special case with type of. It is creating a symbol type of the underlying name that's there. Uh, I don't know exactly why works versus the other in terms of the Colton symbol resolution. So I encourage you to go look into that. But the one thing that I wanted to show you with this example, and this is why I want to look at this a little bit more in detail, is list 1 and list 2 actually gives you the full signature of the type. Okay, so when you do type of list 1, you can notice that all of the values are integers, which means the actual underlying type of it is a list of an integer and the list of a string accordingly. If you attempt to actually even remotely create a heterogeneous list like Lisp, you're going to end up getting type of, if I do, don't know if I could do this, but let's create um, another list, find list 3, make list 1, 2, maybe 3 here. We should get an error. Okay, this is what I was expecting when we attempted to do this, but it looked like it was allowing me to create a heterogeneous list in the bottom there because the type inferencing is now was not kicking in. So this is what you would get if you attempt to try to create, a list of different types. This is not only including string types, but it also includes floats. If you try to do this, it's going to make sure that it doesn't go an upcast. Just like in Haskell, you have to explicitly provide an integer constructor or some way of actually casting it down to actually go in and grab what is necessary. So like in this case, you could possibly just do like say a floor of O, and probably this might work. And as you can see here, list 3, 1, 2, 3. With lists, you have this interesting thing, which is, and again, we can go ahead and do what we were trying to do before, which is leverage the match syntax. So let's go ahead and try that again. In this example, we're just going to check to see if a list is empty, and then from there, we'll probably try what I was trying to do before with wrapping, uh, grabbing an unwrap of an optional integer, and we could do that too as well. Here, to check to see if this is cons, we can actually, let's say that we return, say, shoot, say true here, and otherwise, we do, if it's a nil, notice the nil is capitalized, not lowercase. We'll just return a false. Okay. It's not of type string null. Interesting. Let's see, do this. And let's go ahead and create this with strings. Not empty. Oh, wait. Shoot. 1 second. I just realized it's because I did not. Shoot. 1 second. This be slurp. Weirdness expression. You match LST. All right. So if we look at type of is empty, I'm hoping we get that. Good. So you see that it's getting a list A empty. If we try to, and we get to return a Boolean, if we try to provide, let's say, make a list with nothing, and we'll see it's a nil. If we try providing one of our other ones, it is returning the appropriate Common Lisp T. Every time you will get either a T or a nil, even though you provided true or false, because it's reducing to Common Lisp. This is something that I'm just trying to kind of bring home. Let's come up with another example with match syntax. Let's do the same thing that we did before. Let's try to unwrap our unwrap optional is what I'm going to call it, and it'll take in an X. All right. What we're going to do is we're going to do match X. Okay. And all this is doing is if there's a sum X underscore sum X should be able, it should be fine, but we will see if that works. Let's do this, and let's see none. So let's try to unwrap optional, divide 1 by 2. See this, invalid arguments 2. 3. Interesting. Coalton. See if I could do this. Okay. So it requires me to actually go in and it will leverage whatever it does to actually go and grab that information. So it won't allow me to actually go and unwrap it. It will unwrap it itself. That's kind of sad. I was hoping that I could actually show you guys how to unwrap that. Let's do one more thing. Let me just sure this will not work because this is a fraction. That up. Okay. Let me just do this. Let me see if that works. No, because it's already unwrapped at that point. Okay, that's kind of disappointing. All right. Let's move on. This is particularly interesting. Ah. Let's do. This would be an interesting example. So this one is another particularly interesting thing to show off. See if I could do it this way. Let's create one more function. Let's declare foo as a function that takes in a string and returns optional integer. This is an example from the hoping I could write this in for reference from the coalton reference. I'm going to try and see if I can leverage this to show you guys what I was talking about. Okay, let's go ahead and define foo x, and let's just map +2 into parse int, and let's provide our string. Okay, good. Now let's see what happens if I do unwrap optional. Yeah. And what I'm going to do is I'm going to be even more. Actually, this is fine. See what happens if I do it this way. Let me see what the signature is of our optional. Okay, it's taking an optional of an optional, and oh, it's flattening. I just made flat map. That's not what I wanted to do, but that's okay. Let's see what the. Okay, let's see what happens if I do this. Unwrap optional. Let's do foo of 2 happens. Or is not of type optional. Of course it's not. But if I do a, this should return none. Okay, so at least optional can work with the first level, but because the function is already unwrapping it for us and returning it, it's going to spit out something else behind the scenes. So I have to essentially do some checking to see where's one versus the other. These are the kinds of things about this library that I'm just discovering as we are going along. there's just a lot more about this library that I keep on discovering every day, every time I'm using it. The more I'm using it on a day-to-day basis. Obviously, this is not good for you guys because you want a little bit more understanding on what's available, what's not available. But again, because this is pre 1.0, some of these are legitimate issues that need to be fixed, and some of them are just issues with the documentation uh, that don't necessarily match up the current state of what's in the library. So you're going to have to just keep track and make sure you're up to date with the latest version of the library. Since we've already introduced pattern matching, I'm just going to say one more example from this, and I don't think I've come up with this, but pattern matching at its heart is basically what you saw before, which is it takes in some sort of pattern and to be able to deconstruct the underlying uh, arguments in such a way that it fits in a particular structure. And if it does, it will then use that as a way to look up the particular handler to actually go in and, handle that specific strategy. Okay. Now, what I'm just describing right now is pattern matching when you're talking about function arguments, especially when you are defining functions using the match expressions that we are seeing earlier. Um, as you can see here, this is an example of a function that ends up taking a match expression and then be able to deconstruct it based on the cases and based on what we've seen. It will go ahead and return true or false. But obviously that's not really a good example. So let's go back to what we discussed last week with our color example, right? Let's say that we want to create a function that takes in a color and returns a string, right? This is something again that's part of the current color to string. Sorry, the current library. Um, and of course, that's something that needs uh, to be accounted for. But here we have color to string, and it takes in a color and returns a string. This is an example straight out of the coalton reference that I'm just showing through that allows us to get more in tuned with the writing function signatures, and this is kind of what you would want to end up leveraging when you are designing your functions. You might do some prototyping in Common Lisp, figure out what functions might be available once you define the particular data types, move those up into concrete types, define your function signatures, write up your functions in Colton that's leveraging these function signatures, and then maybe even take a step above that. Once you have defined a set um, of types, you might be able to define type classes, and then at that point you are just uh, uh, furthering away and abstracting away different parts of your architecture where you're defining now interfaces that can be worked on parametrically, and you'll have more generic algorithms at your disposal because you are now using type classes. So we're just working our way up now with this kind of design here. So in this example here, we might define color to string, and it'll take in a color C, all right, and we'll go ahead and write our match expression on C. And we have three cases that we need to really think about. Obviously, you may want to define your function like this. You have red, you see red, blue, you see blue, and then of course green, you see green. Okay. This is certainly one way of defining your function, and you can see that this will all work if you go ahead and do color string red. You'll see that you'll get red, and green, you'll get green, and so forth. But since there are three cases, obviously you'd want to be able to have a catch-all case, right? You can actually do that by just doing underscore, and this is kind of like your default case. All right. Let's see if this works. Okay, this compiled and loaded. Let's go ahead and write this. Do blue, you'll see blue. If you do type of blue, you'll see that it's color. All right. If you type of green, you'll see also that it's color and so forth. You can see how it kind of matches that kind of thing. Now, Colton's brings us several conditional expressions, and I'm just going to just point this out, and then it looks like we're running a little late here, but that's okay. We started a little late, so I'm going to just touch these last two topics fairly quickly, just so that you guys are aware of them. Colton does provide several expressions that we're all familiar with. One of which is obviously if and if and or some of the relational operators, as well as a prog n. Okay. Um, One thing to recognize about this, and this is important though, is the if expression is more like an expression than a special operator when it comes to Colton. It kind of matches the same sort of kind of idea that Haskell has in terms of if expressions. This means that you will end up having an if and else case with an expression, but it is an expression at the end of the day. Okay. It can be used instead of match uh, to have a shorthand for working with booleans. So if you do if, you'll see our expression is just going to be an if and else, right? So let's if we define, say, a um, let's say we've defined our good old standard is even or is odd kind of like thing. So if we have an is odd, you could see that if we have 0 and x, we're returning false. Otherwise, we are returning essentially, you know, um, is even minus 1. Okay. And let's go ahead and define, is even is if we use 0x, we have true. Otherwise, and you see that this is all compiling, and we can actually go ahead and look at type of is odd. Let's go ahead and take in an integer and return a boolean, and we can see that if we pass in, all this all works. The main thing is the expression syntax is very, very familiar to all of us who actually use if in Common Lisp. We also have cond in Colton. I don't think I'm going to have to, introduce cond here. It's the same as in Common Lisp. The only thing that you need to be aware of is it can take in booleans, and the signature um, will act accordingly. So the default, instead of it being T for like cond in Common Lisp, you'd want to use, say, true. Um, and uh, and of course, I won't go too much into more detail other than that. Uh, Another thing to be aware of is there is a prog n in Colton, but it has a slightly different thing than what prog n in Common Lisp does. Okay, I'm going to show this with a quick example. let's say that we have a function, let's call it f. It takes in two integers. This is straight up from the, I thought this was an interesting example in the docs. Let's say that we have a function f that takes in two values and returns you know, their their strings, all right? And we're just going to concatenate them together, all right? They'll take a string representation and concatenate to them together. Now, what you could do is you could use prog n here, and you can actually define let syntax. It has actually a let syntax. But instead of let being like we normally do, you could actually do let x equals. It has a little mini language, and you can specify, you know, overrides. So show x, show for folks who are available, who know Haskell. This is the show type class that will convert any type into its string representation. Um, and you can actually have this syntax to allow you to go define local variable scoped. And then, of course, you can then call, you know, string operations on them like this. And we could see that this, sorry, um, we go run this and you could see that, oops, um, yeah. Unbound show, 1 second. Uh, show should exist. Why is it not showing up? Give me a second. Let's go into here and do an apropos bill and do show. Let's see what's available. Let's be link. Interesting. Show does not show up when it comes to coalton. Interesting. Where is it? Maybe I have to specify the coalton library. Okay, it's not giving me syntax completion here. Let me see here. Open library colon. Hey, it is available here. So do I not have it in? It's not showing up in that for whatever reason. Keep it in mind. Where are you? And keep it going. Here we go. See if I could do it this way. Unbinding of show and definition of x underscore and function definition of f. Unknown binding show. Okay. Let me see if I can define this on this side here. Let's do. The problem here is I don't believe I could just do a simple declare like this in coalton on the top level like we would normally do in in Haskell. They don't have a block syntax as far as I know. Maybe I could do a coalton top level here. Let's see what happens. Okay. Oh, sorry. Define, declare. Now define g, x, y. Let's see if this works. And if this works, then obviously we need to deal with that. Okay. Show x, let y equals show library y. I shouldn't have to actually specify because this is actually in use in this package, but this might be the problem. Let me see though if I can just do it without it, because I'm able to do this with other things. Okay, so it's not able to. Let me see if I could just call first show x and y here. Show x, show y. Unbinding show. Okay. Sorry. ACL describe open library show. Show is a symbol, but there are no values associated with it. Okay. So that just tells me that potentially there is no uh, definition of the type class for X, which is interesting. Okay, let me try another thing then to show you guys this. We could certainly do this. Let's go ahead and create this as being, instead of this, a tuple of integers. We've seen tuples before, which is why I was trying to use this other example, but you know, it for some reason was not working. So we might have like say a product here, and then let's go ahead and we don't need to do this here. Let's just do that. And this should actually go and convert as it did, which means now if we go and, first, let's check the signature. You can see that it's taking our tuples. If we pass in F12, it's going to return the tuple object. Okay, comment. Show may be in the test code. Yes, show may be in the test code. Let's go in. We could certainly go and look at the show type class in the test code. That might be a good idea. Let's see. I didn't believe it was in the test, but I could be wrong. I'm going to, let me see. Let's see. Well, it says that it's there. So I'm a bit disappointed, but we could certainly do this. Coalton test, I think it's called type inference tests. In here, there is a test called um, oh, that's right. I should have actually tested this. Test system coalton. CL user is unbound. Of course, it's unbound right now. Can run this guy. Set package CL user. Then run. Oops. Let's do this again. There we go. I may have just blew away my Lisp. This happens sometimes. Scale adjust here. Okay. Load. And okay. Let me do an as of test system here. Okay. Why is it asking for my package? Hold on. Hmm. That's really weird. I don't know why it's asking for my package. It might be that the fiasco test was expecting it's taking the last image test run of Colton and then running through it, which is a bit dumb if that's the case. But you know, mm, let me start Lisp and then we'll get through our last thing. Oh, right. I have code in um my main.lisp that does not work. And it's related to this guy. Okay. And if we go and try and run this guy, please only define secondary systems that are not in that file. Okay. That's weird. Okay. I will do this one more time. Set package AFP coalton. That's our debugging portion of the of the program. um, seriously, experimenting with some of this is kind of a joy. But obviously, you folks are looking for some other material too as well. So I'm going to go ahead and quickly end with. I thought I would get through type classes today. I kind of figured that it may not be the case. Um, on lesson one, there is our standard definitions for unless and when for folks who are used to these operators. The one thing to be aware of about unless and when is although they do exist, the documentation says that you don't want to use them a lot. Only use them when you are dealing with stateful operations, just so that I think it has to deal with essentially you are dealing with stateful conditions in there um, and accessing things a particular way. If you're writing a lot of conditional code, you are not actually leveraging coalton the way it is intended, which is honestly leveraging pattern matching a lot, much of the same way that one would use pattern matching in, say, Haskell. Uh, that's one thing that kind of stands Colton apart of other Lisp libraries because although a lot of folks might be thinking of writing code like this, let's say that we have a function f. Let's call this uh, divisible. Sorry, equal to 5. Make things a little. Um, and let's say that we do, you know, uh, unless equal to 5, we error. I want number 5. You'll see here that this will work as defined. If we do, if we get equal to 5, 5, you see nothing will happen. It'll actually return a unit. Otherwise, if we define 6, it's going to throw up an error. If we actually look at the type signature of equal to 5, you'll see that what it's returning is actually a unit. Unit is think of it kind of like nil, but it's a top level. It's an identity thing inside Haskell. It's an identity type. You also have when you know we can say define not equal to 5x when not equal um or say not this way equals x5 because I really don't want to deal with the type signature right now for when. I mean, sorry, of not equal for right now. Um, because it's a 3 argument signature. I have to go and figure that one out. Then obviously we'd want to error out if it's not equal to. And we run this, and we get not equal to 5. 5, obviously we'll get unit. If we do 6, we'll get the same thing. All right. If you're writing code like this though, and you're not leveraging the match expressions and other things for doing pattern matching, you're not really leveraging the features of this library. So keep that in mind when you are dealing with the with your signatures and in your Haskell. I'm sorry, in your Common Lisp experimentation of the Colton library. So with that, I'm going to close out. I hope you all have a good evening. Join us tomorrow for the Haskell study group. We'll be covering quick check, which is a Haskell library for uh, uh, unit testing and fuzzing inside Haskell. And those who are part of our weekly Common Lisp discussions, join us next week when we start talking about type classes and functors. Hopefully, functors, applicatives, and monads, depending upon the times. I will show you then, how to define your own type classes in Colton, as well as defining instances of existing type classes, as well as defining instances of your own type classes. In the meantime, there's a couple of notes here that I've kind of uh, written down related to code um, for uh, regarding some of the limitations we saw with division, as well as uh, looking up, if there's a way of knowing what is available in our Lisp image with regards to instances defined for existing type classes. So this way we could do some exploration when we're digging with type classes. So that's it. I will see you guys next week. Thanks so much for joining.